So we're really glad to have William Kenny in town again to give us some Go talk, and probably there will be some FAQ in the end as well. So yeah, let's give him an applause, and then welcome, William.
Hey guys, thanks for all coming out tonight. That's pretty cool. I really appreciate your time. Who's writing code today in Go more than a year? More than a year. Give me more than a year. Wow, more than 6 months. And who is completely brand new, who hasn't really looked at this language at all? I love when we have such a mix of people at a okay, that's pretty cool. I like to ask that question before we start, because I'd like to get a sense of who's in the room so we can really tailor a talk around the people that are here. Hey, dude. Hey, nice to see you, man. Perfect. All right. So I've got about 5 people that have been doing Go for a little more than over a year, and I had about 5 people who have no clue, never seen Go before. What languages are you working with? You raised your hand for that, right? Depends on what day of the week it is. It's been Ruby. Okay. So there's a ton of, I don't want to take up more than 20, 30 minutes of your time. So there's a ton of little things that we can talk about. It's hard when we have such a big group. So maybe I should talk about why I love Go so much and why I'm so excited about this language and why I just continue to go out and talk about it to try to get more people hooked into it. Now, if I say Go to you, the first thing you're going to think about is what? Concurrency, right? Go is known for what? Concurrency, and Go is known as a language that is super fast, right? You're going to build these products, and it's going to be blazing fast, much faster than anything that you've been building up until now, especially if you've been using your Pythons and your Rubies. I'm not going to say Java, because Java has proven itself to be performant. But you're going to hear that Go is really performant, and you think about concurrency. But what I tell everybody when I meet them is, you're coming to Go for concurrency. This is what you've heard about. This is what you're thinking. But when this language is done, every 10 years we get a new language. Every 10 years I tend to start working with a new language. When this language is all said and done, it's not concurrency that Go is going to be remembered for. It's not. What Go is going to be remembered for is its ability to allow us to write code that can decouple itself from change. It is Go's interfaces and Go's composition that is really going to stand out and become part of the next set of languages that we see 10 years from now. And I want to show you some of that while we're here. Even if you haven't seen any Go before, I think you'll enjoy seeing some of this composition code to get a real sense of what I mean. Because this is the stuff that you will use every single day. The concurrency, when I'm teaching, I try to explain, let's stay away from this stuff. Concurrency is hard. It's complex. It's going to create problems for you. We're trying to simplify our life, not make it more difficult. Now, for those of you who are experienced Go developers, you now have a responsibility. Who's ever in this room who's been writing code in Go for more than a year, I am putting a responsibility on your head. You see, Go is only about 7 years old, which means that all of the Go code that is ever going to be written, majority of it hasn't even been written yet. What we've just learned over the last 7 years is just scratching the surface on what are good practices, how do we write code in Go that is the right way to do it. We're just learning. And so for those of you who've got over a year of experience, you have a responsibility. You have to teach the next generation of developers who aren't even here yet how to write code. Aren't you guys already doing that in your shop? I mean, if you've been writing code for a year already, aren't you already in a position where people are coming to you, asking you how to do things? So there's a bunch of questions I love asking developers. I'm going to show you some of this composition. But I love asking this question, especially if I'm going to have a beer with somebody. How do you know when code in Go smells good? And how do you know when the code smells bad? How do you know when you're looking at a piece of code in Go that this is just wrong? How do you do that? How do you build a vocabulary around that? How do you teach that? Now, if you're coming from languages like Java or C# or your typical object-oriented programming languages, and I see this about once every 3 months. About once every 3 months, what happens to me is somebody will reach out to me on Slack, and they will say, Bill, I'm having a big problem. And I'm like, okay, what's going on? And they'll show me a piece of code that looks like this. And as soon as I see this on my screen, I begin to cry. Because here's a developer who's coming from an object-oriented programming language who is now trying to take everything they know from that language and move it into Go. Now, I might be one of the few people on the planet that will say that Go is an object-oriented programming language. It actually is. But we don't want to write object-oriented code in Go. Don't have time to explain that. But as soon as I see this, I begin to cry. Now, I do also have to say this. If you guys can think of a great software product that requires animals, I need you to tell me right now, because about 90% of the code's been written. We just got to assemble the last little piece, and we're done. Okay, we can get up and run in about 3 months. But it's always animals when it comes to this stuff. Now, what's happening here is they've learned about embedding. They've learned how to do type reuse in Go. They're only thinking about type reuse in Go. And they start to fall down this trap of class hierarchies. We've all been taught how to reuse types, reusability around class hierarchies. And that works in a traditional object-oriented programming language. But it doesn't work in Go. And so as we look at code tonight, what I want from you experienced Go developers is start to ask the question, does that smell good? Does that smell bad? Why? And can I explain it? And for those of you who are new to Go, I want you to listen to the things that I'm looking at, the things from a code review start to make my head spin from a Go perspective, and hopefully learn a little bit of why it doesn't work here, and we'll walk through some other code as well. So immediately, I see this animal struct, and I'm going, oh my God, here we go. They're trying to create a base type, right? This base type of common state. And it makes sense. Here's an animal name and is mammal. But immediately, they go, okay, we can create methods in Go. Just you have methods in all these other languages. Here's a method in Go. It takes this animal, and they create some implementation that an animal can speak. And if we look immediately at this method, my brain says, we're never going to call this method. The implementation is completely useless. It adds no value. They're implementing it, but it adds no value. That's my first smell to all of this, outside of the fact that animal looks like a base type. Okay, I keep going, and obviously if you're going to have animal, we're going to have dogs, and we're going to have cats. I see this every 3 months. And so here they go, they create their dog, and on line 32, you see embedding in Go. And embedding is that equivalent to your inheritance in the sense that we can take that animal type, we can embed it inside that dog, and now dog is everything an animal is. There it is. Everything an animal is in terms of that state. And they do this, and they say, okay, this is great. I know how to do this. I've got my type hierarchy right here. There's that animal, there's the dog, and this dog can speak. And they keep doing this, and they're feeling good. And suddenly, they get to their cat, and they're like, okay, I can do this with cats. A cat is an animal. I'm sharing all of that state. There it is. And they implement that speak. And then this happens. This is when things fall apart. You see, in these object-oriented programming languages, what type hierarchies are doing is they're saying the following. Let's group types together by their common DNA. If these two types here, these derived types, have this common base type, this common DNA, then we can group them together. But this doesn't work in Go. Just because cats and dogs embed animals doesn't mean we can have a list of cats and dogs by their common DNA animal. This is where things start to break down. And this is when I'd like to explain how Go's philosophy is a little different. Those object-oriented programming languages are having us look at type and having us work with concrete types and to group concrete types together by that common DNA. But grouping types by a common DNA is ridiculously limiting. I mean, think about it. If I wanted to be part of a group with you, we have no common DNA at all. You and I could never be grouped together, ever. There is no common DNA. It is restricting. But there's a couple of things here. What if we could group ourselves together, not by a common DNA, which we don't have, but by the things we do, by the things we love? What do we both do? There's something that we know we both do because we're sitting in this room. We both like to program. I can find something in common with each and every one of you by something that we can both do, that we both love to do, which means we can all in this room be grouped together. There's a huge amount of diversity in here when we think about what we do and not who we are. And Go has taken this philosophy here as well. Let's stop thinking about our common DNA and what we are, and let's start thinking about the things that we do that bring us together. We can't do this in Go. This won't work. So how do we go ahead and teach this developer to think about grouping things by what they do and not by what they are? Well, the very first thing we're going to then start learning about is that interface. That interface is no different than any other language you've programmed in. The interface develops what? Defines a contract of behavior. No big deal. Doesn't matter if it's Go. Go is not trying to be novel. In most cases, Go is not trying to be novel. You know how to program in this language pretty effectively. There are some things you have to learn around projects and code structure. And like I said, these type hierarchies have to go. But that interface is just a contract. Nothing novel there. And maybe there's some idioms around calling it a speaker and it has one active behavior, speak, but there it is. We know that dogs and cats can come together because they both know how to what? Speak. Forget about that common DNA, man. It's no good. We want diversity. We want flexibility. And so I can get rid of that animal type. I really don't need it. That animal type was providing 2 fields of state. I mean, a little copy and pasting can go a long way. Don't get me wrong. If there were like 10 fields there, I might keep animal, but I would never implement this speak interface around it. But there may be, so I'm going to get rid of it. All I care about are dogs, and all I care about are cats. And what we have now is this dog implementing the speaker interface just by that method. Something else that's really interesting about Go is all about convention over configuration. Go wants you to write the code, and the convention of what you're doing in that code dictates things. In this case, the fact that this method exists, has the same name, input and output, which is nothing, means that we have implementation here. I don't need the keyword implements. The compiler identifies this for us. And now this dog knows how to speak. It's implemented the speaker contract. So is this cat. This cat has implemented the speaker contract. And now I can group dogs and cats together through what they do, not through who they are. And I think this is a really important design principle that people are missing in Go. This is what Go is going to be remembered for at the end of the day. The power behind thinking about what we do and not who we are. And when you meet that developer who's coming from that object-oriented programming language, and they start writing code like this, which is not their fault, this is how they've been trained, here's an opportunity to start teaching about pulling away from that type hierarchy and to think about behavior. Now, that's all simple and easy. We can do that. We've got an example. This happens to me every 3 months. It's going to start happening to you as well. The more you learn, the more new people that start entering your shop, the more you're out talking about Go, you're going to see this over and over and over again. Right? And these are opportunities to teach. But like I said, it's Go's ability to decouple itself from change that I think is the real power of the language, not the concurrency stuff. The concurrency stuff is cool, but it's not the stuff you'll use every day. I mean, think about it. You should be writing code for today, but designing code for tomorrow. Write code for today, because every line of code you have today is code you have to maintain. That is technical debt. You have to deal with it. Writing code today that you're not using is just adding more technical debt to the issues. It's adding more problems. But we have to design for tomorrow, and not through these large abstractions that hide the cost of things, through a minimal level of decoupling that can adapt to change and allow us to still write code that's performant. So how do we do this in Go? Where does Go take us here? Well, Go takes us here through the use of composition, and I want to just briefly show you, without getting too deep in the mechanics. For the guys that are here in my class, we're going to go deep into the mechanics in this tomorrow, but you'll start to see a little bit of why I really love Go. So let's start with a simple piece of code. Now, a lot of times, I see way too many developers, when they're about to solve a problem, think about the contract first. It's easy to think about, okay, what are the contracts that I need in this code in order to solve this problem? And immediately when I see that, I put my foot down. I say, stop. I've asked you to solve a problem. We're not, unless somebody here works at Google, I don't work at Google. I don't have 6 months to play research to be able to solve problems. I'm asked to solve problems immediately, as quickly as I can, which always lends itself to the next question I love to ask developers. The first one is, how do you know when a piece of code is readable? How do you know when a piece of code smells right and wrong? That's the first question. The second question I always ask a developer is, how do you know when you're done with a piece of code with an API and you're ready to move on to the next one? How do you know, as a technical manager, it's time to tell that developer to move on? How do you know yourself it's time to move on? What are your design philosophies around that? What are you looking for to determine that? Now, normally when I ask that question, I get one answer, which to me is partial, which is, well, if I ask somebody in this room right now, how do you know when you're ready to move on from this piece of code to the next? Who's going to give me a quick answer? It's going to be the answer I always hear. A lot of times I hear, well, when all the tests pass. Well, as soon as all the tests pass, then I'm done. I can move on to the next problem. So if you're going to say tests, then I'm going to ask you, okay, how do you know when you're done writing all the tests? What's your philosophy around test coverage? How do you know when you're done? What are you looking for? How do you know when you're done writing all the tests? Okay, so do you guys think that every piece of code, every package, every should have 100% code coverage before you move on? Because that's not possible. That's an impossible task. And even if you get 100% code coverage, what does that mean? It means you have some scenario that runs through every line of code once, which doesn't really mean that everything is 100% every edge case working. So 100% doesn't work. So what should the numbers be? I can tell you what my numbers are from a design philosophy. I ask my developers this. I want 100% code coverage for the happy path, positive path. When everything is really good and life is good, I want 100% code coverage for that. But overall, if you can get me 80% code coverage, I'm okay with that. We will move on. And over time, we'll learn more, we'll fix bugs, we'll add more tests, and maybe it will go up. Okay, but I told you that's only part of the story. Now you feel like you have enough code coverage, but can you move on? And the answer is no. You are not allowed to move on if you work for me unless you can answer this question. What can change? That's what I'm going to ask you. You've written a piece of code, it works, it's functional, we'll go put it in production, but what can change? What change is coming, and can this code adapt to that change? Now, if you say to me, Bill, nothing can change. We're handling everything. We're done. We're going to move on. But if there is something that can come to us, change, we have to deal with it. That's the decoupling. We cannot write code where if we have to change one thing, we have cascading changes across the entire code base, because that's going to create instability and chaos. I don't care how many tests you have. So how do we answer that question? I'm going to go through an exercise here on how I do this. Now, over time, you're going to get more experience. You're going to know where you need an interface right away and where you don't. But let's say we don't know about the contracts right now. Let's say I was asked to solve the following problem. Let's say a client comes to me and says, Bill, look, I've got $1 million contract on the table right now, but we cannot sign this contract unless we can do the following. You see, I've got a system out here, and that system is called Xenia. And Xenia has this database of really valuable data. But our client uses this front-end API we have called Pillar. It's a whole set of front-end APIs that they're building apps on. And they've come to us and they said that data in Xenia is really valuable. And oh my God, if you could put the data from Xenia into Pillar, and I can access that through the front end, I'll sign this contract right now. This is what I need. Hey, Bill, can you move the data out of Xenia and into Pillar? And I look at it real quick and I say, I think I can do that. I mean, we're just moving data, and everything we do is just a data transformation anyway. This is just one big transformation over the wire. Yeah, I can do that. Hey, Bill, how long is that going to take you? I love that question. Because it depends. You see, if you're the kind of technical manager that every time I solve a problem and get it in production, you make me move on to the next problem, I'm going to take 2 weeks to solve this. Because I know I have to wait 2 weeks in order to make sure that it's done, because you're going to make me move on to the next thing. But if you let me give you a solution that will work, let me go back to my desk, let me refactor that code, let me make sure that it is done, that we've adapted, we've dealt with change, I'll give it to you in 2 days. You can start solving this problem in 2 days. What would you like me to do? What are they going to say? 2 days. And I'm going to hold them to it. So let's do that. Let's solve the problem in 2 days. Do I care about contracts? Absolutely not. Do I care about decoupling? Absolutely not. What is the problem I have on the table? Move some data out of Xenia into Pillar. That is the problem I need to solve right now. Let's solve that problem. That's the only problem I care about. Okay, so we go to our desk and we do the following. We say, okay, here's some data that we're going to move. I've made it really simple. It's a data structure. We can rip that out. Some of the code here is mocked, but I want you to look at the structure. The implementation is irrelevant. This is the structure. I want you to look at the pattern, the design philosophies here, how we're leveraging, refactoring, what we're doing. Here's the data right there, the data structure that we're going to move that data in and out of. So what do? Right away, we create a Xenia type. Of course, Xenia, we got to learn how to connect. You see, all you guys ever watch that movie, The Martian? It's one of my favorite movies. The Martian. You've all seen The Martian? What does he say at the end of that movie? Most important line in the entire movie. He says it at the end while he's in the classroom with all those students. What does he say? He says you got to solve one problem at a time. One problem at a time. And if you solve enough problems, you get to go home. I need you to start thinking about this. I don't care about how immense this problem is. We break it down. We solve one problem at a time. We build one piece of the API at a time. We build on top of things, and before you know it, you've solved your problem. And so right now, I care about one thing. I only care about one thing. I need to connect to Xenia, and I need to pull some data out of Xenia. And right now, if I can at least pull one piece of data out, life is good. Because I'm going to run this as a cron job. It's going to run every 5 minutes. We're going to see what data we haven't pulled. We're going to pull the new data out, and we're going to get it into Pillar. I'm going to keep this thing as simple as I can, and we're going to get this done in 2 days. So I have the first problem. How do I connect to Xenia and pull one piece of data out? So I've got the information that I need, host information, timeouts, all that good stuff. And I go ahead and I design the pull method, which accepts a data value and goes and hits that Xenia system and pulls that piece of data. I've mocked it out with a random number, no big deal. And I'm mocking out end of file, I'm mocking out networking errors, and I'm mocking out data. But when this method is done, I know how to connect and get a piece of data out of Xenia. I've solved my first problem. Same thing with Pillar. I need to connect to Pillar and store a piece of data in Pillar. So the only thing I care about. Everything else is irrelevant to me, one problem at a time. And we go ahead and we do this. I'm just writing the standard out to simulate this. I now know how to pull data out of Xenia and into Pillar. I'm not done yet, but I've solved these 2 problems. That was hard enough. And now the next step is pulling one piece of data is not enough. There's going to be a lot of data I have to pull. So how do we pull a bunch of data out, and how do we know when that's all done? We've got some of that already. And how do I build an API around that? So the first thing I do is I build this type. Here's that system type. Now this is embedding again in Go. I'm saying that a system is composed of a Xenia and a Pillar, something that knows how to pull, It's something that knows how to store. I'm using composition here. I'm using the ability to say that this system has both of these pieces together. And we're going to use this system to be able to move the data in and out. Now, I create a new function. It's called pull. And I have a question. I used types for Xenia and Pillar with methods, and I'm using a function for my pull. Why do I believe that functions provide you better readability than methods ever will? Why do I like to use functions over methods when I can? Why do you think a function can provide you better readability, both in the code and later on when you're debugging? Think about this. A function requires you to pass all the input in and to return the output out. And if you write your functions properly to not hide information, you know exactly what's going in and out. But a method always has to operate on a value. And does the method signature indicate what fields you're working against on that value? Technically, that information's hidden. If you can write functions that don't hide the cost, and I'm even talking about not necessarily always passing the address of a full struct in. What if you're only using one field on that struct, and you're passing the whole struct in? You've lost information. You've lost it. It's no longer on the function signature. It's no longer in a stack trace. It's gone. All for what? Well, Bill, I want to adapt to change, and so if I pass the whole structure and the structure changes, I can deal with that. No. Refactoring's a good thing. I had somebody tell me, Bill, refactoring's bad if you're right. If you're refactoring code, that means you're making mistakes. You're doing all this stuff wrong. I said, dude, what are you, high? If I'm refactoring code, it's because I'm learning and I'm improving what's there. Refactoring is a positive thing. It allows us to improve the code. I don't buy into that. And so if I'm only using one field in that struct, I'm not going to pass the entire struct through. I'm going to pass in the data field that I need. I'm going to make that function more readable. But here's pull. What does pull say? Pull says, I know how to pull data out of Xenia. Give me a Xenia, please, and give me this slice of data, this array of data, in a sense, for those people who are new to Go here. Give me this array of data, this slice, and give me the Xenia, and we'll range over every element in this array, and we'll call pull against that Xenia, and we'll populate it. No big deal. If you give me this slice of 100 elements, we'll pull 100 out at a time. I'm composing on top of the API that I already have in terms of Xenia. I love doing that. I cannot tell you how many developers miss the boat on this. Your APIs are going to be multi-layered. You're going to write lower-level APIs and higher-level APIs to make it easier for the developer to use. But if you compose your lower-level APIs for the developers to use as well, and you give them the ability to use both, you've given them the flexibility to have more control over what's happening when they need it. And if they want more of you to do the work, you have that higher-level API. Think about API composition as well as everything else. If my user wants to use Xenia directly, they can, but I've also given them this ability to do some higher level pulling. Pull knows how to pull all the data out of Xenia in one shot and return how much data we got per slice. Store's no different. Store knows how to work with Pillar. It says, okay, here's all the data to store, range over that, store that data in Pillar, and then let me know how much of that data we got in or if we got an error. And finally, copy. Now, copy's interesting. Copy takes a system. What is a system? Remember, a system is the combination of what? Xenia and Pillar, the two systems that I care about right now. And so copy does it all. It creates that slice, and then in that endless for loop, boom, 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 just start pull, store, pull, store, pull, store, pull, store, pull, store over this batch, blah, 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 blah. We're done. We're done. We move on. We're done. And if we look at main leverages this API very, very quickly. It comes in, it creates a system. We create that Xenia value, we create that Pillar value. We can imagine we're setting up hosting information and stuff. Not important here. What's important here is the construction and the mechanics. And then we call copy passing system. I wrote this code in 2 days. It works. Remember something. I teach a lot about if performance matters. But performance don't matter until you got something working. I teach a lot about if performance matters. But we have to get things working. And if it's fast enough, we're done. Okay, so we finished this code. I put it in production. Data is now moving from Xenia to Pillar, and they sign the contract. But I've written this entire program in the concrete. This is what I said to you. In the concrete, I solved the problem. Now I go back to my desk, and I ask the question, what can change? So what can change? What change is coming to this code that's going to require refactoring? We're going to get new systems. Because as soon as this goes in, somebody upstairs is going to freak out and say, oh my God, you know, there's a system out there called Alice that has data too. And if we could get that into Pillar, oh my God, this is a whole, Bill, can we do that? Right now, I can't do that unless what? I do some major code breakage here. I am not decoupled from change just yet. I shouldn't be. I solved the problem in front of me. The source and the destination systems can change. So let's now decouple ourselves from this change. Let's start to refactor. But what's brilliant is this code's already in production. It's already solving the problem. No stress here. We're going to get this done. So we need to decouple from change. What can change? The systems can change. And if I go back and look at this API, I notice something right away. This function is tied to the concrete. It is bound to Xenia. The only thing this function knows how to work with is what? Xenia. We need to decouple this function to work with any system that we put in place. How do we do that? This is where the interface comes in. But more importantly, is that I am not struggling to figure out what the contract is. The contract came to me. We solved this problem already. The Xenia type already has a method named pull, and the Pillar type already has a method named store. Am I sitting here struggling about what this contract is? No. Very little effort now. I look at those types. I go, those are my contracts. This is what has to, when I declare a new type named Bob, this is what has to be implemented. Alice, this is what has to be implemented. And this interface, the puller interface, says I will accept any concrete type that implements this interface, this contract, a method like this. I will accept any value of any type that implements this contract. So look at what we do. We added our interfaces. I change pull. Pull no longer takes a Xenia pointer. What does pull take now? The puller interface. And now what it's saying is very clear. I will accept any value that implements this contract. Any value. We have the highest level of decoupling in Go without generalization. Did the code change? Did the algorithms inside this function change? Not at all. The only thing that changed was the type for the input. We're taking a puller, and we're calling the pull method against the Xenia that will pull in through the interface on line 87. We did not lose all of the work we did around algorithm efficiencies, around if performance matters. We just decoupled ourselves from the concrete. This is what I mean about thin layers of decoupling and not leveraging generalizations to deal with change. Everything we know about writing performant code isn't lost. But this function is the highest level of decoupling we can get. I can pass any concrete type into this now. And we did that with store as well. Store now also can accept any concrete value that implements that contract and can be leveraged. Brilliant. I've decoupled here. But here's the goal. We want to try to decouple our code all the way down to initialization. This is what we need, and we're not there yet. Because if I look at our next API, which is copy, copy is using what? Concrete type. It's system. Remember what system is. System is using the composition of two other concrete types, Xenia and Pillar, because it knows how to pull and store. But no big deal. Let's decouple copy from the concrete. All we need to do is what? Add another interface. Add another interface. Here it is, the pull store interface. And we can use composition to declare this interface. Let's bring in puller and bring in store together to declare a new interface, solving one problem at a time, one problem at a time. Now I'm solving the decoupling of copy through the new interface that I'm using through embedding, composition, interface composition. That means any concrete type that implements both pull and store implements the pull store interface. And doesn't the copy function require both pieces of functionality? Oh man, we're good to go. All I now have to do is change copy, not the code inside of it really, just copy to say, I will take any concrete type that implements the pull store interface. And what's brilliant about Go, and if I had time, I can show you the mechanics. I can pass that pull store interface value into pull and store, even though pull and store are looking for two other interface types. Since an interface value in Go has the same memory model underneath, a two-word data structure, Go allows for implicit conversion between interface types. So I can take that pull store interface and pass it in because the compiler knows any concrete type sitting inside, any concrete type that implements the pull store interface must also implement the puller interface and must also implement the store interface. It's all there in the type information. Compiler is doing this at compile time. This is one of the most beautiful things about not having that keyword implement. It's not tying our APIs and code. Compiler goes, oh yeah, oh, there's compliance here. We're good to go. Let's do it. It's going to keep this code nice and clean. We can think about what we do and not who we are. We know the concrete type can do pull store, pull and store. And I'm also validating that both pull and store are being used here, and they are. I've just decoupled the three pieces of my API, but I'm not done. I told you I need to get to initialization. And right now, if I want to work with Bob or Alice, I have to break system. Look at system. The system, even though it is already compliant with pull store, it has a pull and it has a store, it's compliant. If I want to use Bob and Alice, I have to perform a code refactoring here. That is unacceptable. How am I going to solve this problem? How can I deal with a situation where this concrete type must be bound to other concrete types, but happen at initialization? And here it is. This is the kicker. This is the piece that I think is the big win for Go, what people are going to remember about this language. Let's redeclare the system type, our concrete type. But let's not embed it with two other concrete types. Let's embed system with these two interface types. Whoa. Think about what I just did here. The system type now says that we can store inside of it any concrete type that implements the puller contract, any concrete type that implements the storer contract. And those two concrete types, whatever they are, must implement pull and store, which means that system is still compliant with both contracts and the pull storer contract. What we now have is the following. We are fully decoupled from change all the way down to initialization. I can now change out line 136 or 137. Don't put a Xenia in there, put a Bob in there. Don't put a pillar in there, put an Alice in there. It doesn't matter. Only now during initialization do I have to worry about code and changing, and this could be read from configuration database, whatever it is. I can run multiple copies at the same time. What can change? The systems can change. Are we decoupled? Yes. Can anything change? The answer is no. We're done. We've got the test coverage I want. We're done with change. Now we get to move on. I want all of you to start to develop a design philosophy for everything you do. Forget about patterns. Forget about frameworks. Forget about all that. They lock you in a box. And when that framework and pattern doesn't work for you anymore, you are lost. I want you to develop a design philosophy so I can ask you any question and you have an answer. It's not about the answer being right or wrong. It's an answer that's based on conscious thought. When are you done writing a piece of code? What's your design philosophy around that? How do you know code is readable? What's your design philosophy around that? What's your design philosophy around testing? What's your design philosophy around decoupling? What's your design philosophy around performance? What is your design? What's more important? Integrity, readability, or performance? What's more important? When is more important? What are the trade-offs? What are the costs? You cannot... Software development is not about writing code. It's not about writing code. The writing of the code is the last piece. Every line of code you write, every function you write, every package you write, every API you write, comes with a cost and a decision, an impact and a cost. Everything, nothing is free. Nothing is free. So how do you understand the costs that you're choosing, and why are you choosing them? What are the benefits? I'm going to leave you with an example of this, because I've already talked a little bit too long. Here's a great example. I love this example about architecting with cost and trade-off. Let's talk about NUMA. NUMA means non-uniform memory access. It's the big thing today in hardware. In fact, from a hardware perspective, it's hard to get around it. Now, what is NUMA? Why do we have NUMA? Why is the hardware all crazy about NUMA? Because at one point, we told the hardware vendors, I need a machine with 100 sockets. I need a machine with 100 processors in it, because I want to start up all these different VMs, and I want to do all this crazy stuff, and I need that. And the hardware industry said, look, dude, if I give you a machine with 100 processors in it, and they all have to go through the same bus to get to main memory, it's just not going to work. So if you agree to this, I can give it to you. Cost trade-off. If you agree to unknown latencies to accessing memory, main memory in particular, instead of always knowing it's going to cost you 100 clock cycles, instead of knowing that when you have a cache miss or TLB miss there, it's going to cost you 100 clock cycles, it may cost you anywhere from 100 to 300 clock cycles, depending on where that memory is. Now, if you're okay with that, I'll give you a machine with 100 sockets in it. And what did we all say? Yes, because in this case, scalability was more important than what? Latencies. We made the trade-off. Nothing is free. This is what we chose. But let's talk about garbage collection in Go. We all screamed at the garbage collection engineers. We all said, we cannot have latencies. We cannot have stop-the-world latencies. My code has to keep running even when garbage collection is running. And the engineering team said, okay, look, if you want your code to keep running while we're doing garbage collection, then the trade-off is you have to take a performance hit. In fact, you got to take a 25% performance hit on your code. Are you willing to take the 25% performance hit? And we all said what? Shit, yeah. As long as my code keeps running, I don't care. I always equate that to like you being in traffic, and the traffic is really dense, and you decide to start taking side roads, and you don't really care how slow you're going down the side roads as long as you're what? Moving forward. And we took that. From a garbage collection standpoint, we said no to latency. We'll take the performance hit. On the hardware side, we said what? We rather take unknown latencies to have what? Scalability. Everything you do, every line of code you write, every function you write, everything you do comes with this cost and the trade-off. I want you to start thinking about that. I want you to start designing and architecting software, understanding the costs and the trade-offs you're making. It's not enough to just write code at some point. You get it to work. But what were the costs and the trade-offs you made to get that code working? And then where can we improve where we need to? So this, to me, is what Go's legacy is going to be. What I showed you here with composition. I didn't really get to show you the mechanics behind it, but hopefully from the other languages, you're seeing that thin layers of decoupling without generalization. Concurrency stuff is cool, it really is. But this is the stuff you use every day. If you want your code to last, not just today, not just next week, but to deal with change over the next 6 months to a year, then this is the stuff. This is the stuff that you've got to learn how to do. What can change? Decouple from that change, and then move on. All right, thanks, guys.
Hey,
Hey, dude.
so I already kind of know the answer for this, but I'll ask it anyways. So what happens if you have an interface and one of the methods either needs to return something of that same type or accept it as a parameter? That can be challenging.
You have an interface that's returning what?
So let's say you have I don't know, let's call it like we'll call it like dog, and it can give birth to itself, right? And it's going to return a new dog, right? But you want something that's like maybe a mammal that accepts dogs and cats and something else. So what's the return type?
From a contract perspective, that contract would smell
Yeah, I know.
really bad to me. In fact, for me, I'm already smelling interface pollution. That is huge interface pollution, right? Especially if you're returning the interface for that big thing. So already that's a big smell. Factory functions are really important in Go, right? We don't have constructors. So we have functions that initialize values and return them.
Yeah.
But you're saying this is coming out of an interface. You've declared a contract as a factory.
Well, there are some other use cases. Like say you have a logger and you have an interface for it and you want to configure that logger, right? So you need to return something. You need to return that thing. Like you can't, I know you can't do that, right? So it creates a challenge. And there's cases, for example, you want to return something, but you need to like bring in the original interface all the time.
See, I love that logger interface. I think the logger interface is the biggest mistake.
Oh, the standard one?
Just
it's horrible.
There's no logger interface in the standard library.
Yeah.
Okay, but when people start talking about logging interfaces, I start to cringe. Logging is a very opinionated thing. Every application has a different constraint, right? In some cases, logging is data. Logs are data. So if you can't write to the logs anymore, your application has to what? Stop. But what if you're feeding video to 100,000 homes and you can't write to logs anymore? Are you going to stop the feed on everybody's television set? Every application has a different constraint. And some packages are allowed to log, and some packages just aren't. Look at the Go standard library. Does the Go standard library log anything? No, if you need to log things around the standard library, what are you going to do? Log before and log after. So I always question logger interfaces because most packages, especially these types of packages that are looking for logger interfaces, because they're decoupled from the application themselves, don't need it. They shouldn't be logging. Now, you might have a package that creates Go routines that are doing things, and there's some things there you want to log. But do I need an interface for that? If I ask for an interface, if I ask you to implement an interface, I've now asked you to implement a type and implement a method. That's a lot of work. Couldn't I just ask you for a function, even an anonymous function? Couldn't I just ask you to provide me a function that I will call every time there's an event, and you can do whatever logging you want inside of that? Yeah. Wouldn't that be so much simpler?
No, I do agree there's other ways of dealing with it, but that like the interface is not the challenge of having a method where you want to return that same interface as an output, or you want to accept as a parameter, I think is a rough spot.
Anytime I see, in general, when I see in general, there's exceptions to everything. We're looking at when does code smell good and when code. Anytime I see a function or a method return an interface type, in general, that raises a flag.
So the case is, okay, you return, say a struct, because you implemented a concrete type, but then that doesn't work if you try to use an interface.
Let's talk on the side, because you've got a really weird edge case here and I'm trying to pull it back into some generalized rules, right? So we'll talk on the side, you can show me the code. But in general, when I start seeing functions and methods returning interfaces, and I've done that, I've got code, there are exceptions to it. In general, it raises a flag, and now I want to start asking what we're doing here. But show me that code when we're done.
Since you advocate for interfaces that mostly have methods or functions rather than data, I'm just wondering, how do you deal and go with generics and basically collections that have those generalized types that actually have data. that you
Yeah,
have
so
to deal
Go
with.
doesn't have generics. Go 1.0 was not going to have generics. Go 2.0 at some point might, but it's not there. So instead of getting into a debate on whether generics are good or not, the people who have tried to solve this problem have tended to do it with code generation. And there's a tool out there by Matt Sherman, who works over at Stack Overflow, basically, who's built a really nice one he calls a typewriter. And it's pretty cool. So the best solutions I've seen to that has been code generation. I'm not a big fan of code generation, but in those cases, I think it can work out pretty well.
That's something that changes your source code? Or
Well, you're going to
exactly
run a
does it-
tool that Go Generate can run, or something that generates the source code you need, and if that code has to change, you're going to regenerate it, right? So that's what I mean there. Now, I could just tell you over the last 25 years of writing code in C++ and C# that have generics, I stayed away from them. The 1 or 2 times I've needed them, I found a way around it. And I do it because I don't think generics provide readability to your code. And you have to be very careful when you decide to trump readability over what you're doing. You have to be very, very careful and conscious of that. And so after 25 years of building business applications, okay, I've gotten around it. I had a business partner who loved them, loved generics. And every time there was a bug in his code, it's yours, son. It's you. I don't want to go anywhere near this code. It's impossible to read. So there's the trade-off, right? You're trying to build some generic piece of code that can work against all types, and I can get it sorting and stuff. I get it. But what are you losing for that generic code? You're definitely going to be losing some readability. What else are you losing? Is that so generalized that you're also walking away maybe from a more efficient algorithm? I don't know. But these are questions I'm going to be asking. So what's the trade-off? I love asking people in a room, I don't think I asked you, does performance in your code matter? Does performance matter? Who's not going to raise their hand if I ask, does performance matter? Yeah, and now I'm going to say you're all liars. You're all liars. Unless somebody in this room is writing code day in and day out in C and assembly, you're all liars. Because if performance really matters, that's where you should be. That's where the gaming industry is. See, performance doesn't matter to you guys. It's nice. What matters more is productivity. It always has mattered more, solving those problems quickly. What's nice about Go is it focuses on productivity, and you get a level of performance you've never seen before at the same time. That's also something that's really special about Go. Productivity has always mattered more. And when you start making sometimes decisions around productivity, you can start getting lazy, and you can start walking away from performant code at the same time. You start generalizing things. So it's dangerous. There's a talk here on data-oriented design, which I talk a lot about. But at the end of the day, Mike Acton is talking about cost impacts and how important data is, and how important writing algorithms that are efficient for the data transformations that you're performing, and not generalizing these algorithms at all, but understanding that you're writing an algorithm that's very specific to the data you're working on and the data transformations that you're trying to perform. And at the end of this talk, this young kid comes up to the mic and he says, Mike, what you're telling me is if the data starts changing, I have to rewrite all this code. And Mike looked at him and he said, of course you have to rewrite the code. If the data's changing, your problem's changing. And if your problem's changing, your algorithms have to change. So what's the shock? And most of that shock is coming from being taught to write generalized code to the extent you can to decouple from change. And what I tried to teach tonight is forget about that. We can leverage the interfaces to decouple from change without having to write generalized code and to walk away from both performance and readability. But that's just part of my design philosophy. You got to develop your own.